Hi, today we're covering key features of an exponential function. So what is an exponential function? Well, it's got two parts to it. One, it has a horizontal asymptote because there's nothing you can plug in here that will make it negative. So knowing that, we know it will never cross the x-axis. So we have a horizontal asymptote right here. Now there is a key point. The key point is when this is 0, because anything to the 0 power is 1, and that's basically your y-intercept. So we put a dot right there. Now, since 2, that means every time it increases, it doubles. So our graph should look something like this. So basically, since 2 is bigger than 1, we basically get an increasing. So if this number here is greater than 1, it increases. Or as they call it, a growth. So this one right here is the opposite. So same thing, it's still got the, cannot be 0. But the trick is when you put in 0 here, this is your y-intercept, is a number in front. So we put a dot at 5. But as 1/5, as it increases, it's decreasing by a fifth, or again multiplied by a fifth. So this one actually goes like a downhill slope. Okay, so if this is a fractional, if this is between 0 and 1, this value right here, then it decreases or decays, if you will. That's what they call it. So this one's a growth function, that's a decay function. So go ahead and look at this one. And try this one. So let's talk about the transformations of it. Basically, to graph these, we do the same thing. So all we got to do is draw the graph. And so first and foremost, it has a horizontal asymptote right here. Now this one, if we plug in 0, we get -1. So this right here is where this dot would be. And since 3 would typically be increasing, like that, because it's negative, it's flipped. So it's the flip of this, which looks like that. So the question is, when does the horizontal asymptote change? The answer is when you subtract or add by it. That is your new horizontal asymptote. So if I take a look at this, -4 will be my new horizontal asymptote. Now, if I plug in 0 here, I get 1 minus 3, which would be -3. So it's 1 above the horizontal asymptote. And since 3 is bigger than 1, it's a growth. Go ahead and try that one. Okay, how do we model? This is used a lot in so many different areas, especially with population. So it says right here the population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? Well, the way it works is we have a growth and decay. So the growth formula works like this. So we've got our population. So we're going to start with the starting amount, which is 4.6 million. And now it's going to grow at a rate of 1.3%. Since it's growing, we go 1 plus 0.013 to the 4th power. So the reason we put the 1 is because we got to include this and then increase it every time by 1.3%. So if you plug this in the calculator, basically we get 4.84 million. It grows rather quickly. And now what happens if we keep the same way and we go to 2040? Well, it's based off of 2010, so our new number is going to be 30 instead of 4. So we're going to do the exact same thing. To the 30. And that would be 6.78 million, which is quite a bit. Go ahead and try this problem. So now this brings us to exponential growth and decay. What growth is whatever rate you're given, you add 1 to it. So if the rate was, let's say, 0.2, it'd be 1.2. So let's use that. Rate is 0.2 or 20%, same thing. So if we do this, if you look at this model, let's say we start with 10, it'd just be 1.2 to whatever t value is. But if we're talking about decay, which decreases, we're taking away 20% at a time. So if we're taking away 20%, we're left with 80%. So if you think of this one is closer to 0.8. So when you talk about growth, it's above 1. It's 2 above 1. But if you're talking about decay, it's 2 less than 1. So just keep that in mind. Just make sure you read for decay and growth. Go ahead and try this problem. Try this problem. Try this problem.